So this is part D of homework 2, and what we got today is we're going to be expressing our heat diffusion equation that we found in part C as an algebraic equation via the Crank-Nicolson differencing, and we're going to be using the von Neumann stability analysis to show that what we found is stable regardless the choice of our R value, which is given in that second step. And then I'll explain the the collab stuff later on, but we're just going to get started. So I have our equation that we found, or that we have from part C, and if you remember, we did expand this into more of a matrices form, so we can go ahead and write that down. N plus 1 minus j plus 1 over delta t, which equals our alpha times our matrix, and it is tj plus 1 n plus 1 minus 2j, or 2tj n plus 1 plus our tj minus 1 n plus 1 over our delta x squared. And then we're going to add this to, so this is our n plus 1 iteration, and then we're going to do our n iteration, j plus 1 n minus 2j n plus tj n tj minus 1 n over delta x squared. So next what we're going to do is, looking at this alpha value, we've been given an R value to substitute it with. So that R value is this right here. So we're just going to go ahead and substitute and then sort of simplify this equation down further. So what we're going to be left with, oh, and by the way, forgot to mention, so this is supposed to be tj and j and n plus 1 and n. Oh, my bad. What we're going to be left with is tj n plus 1 minus, I believe, r. So this would be tj plus 1 n plus 1, and then minus tj minus 1 n plus 1, where so those would be r, where we got this. Basically what we're doing is we're just multiplying the r's over, since there's a delta x squared, we just get rid of that, and then we're just kind of massaging the equation out essentially. So just taking all these n plus 1s, moving them over, and then taking the n's and moving them out. So then we're left with tjn plus r tj plus 1 n minus 2r tjn plus r tj minus 1 n. Yeah, I believe that is correct. One little error, I forgot that we forgot this value right here, so it's supposed to be 2r tjn plus 1 plus all of that. And now we can just go ahead and simplify it. So we have 1 plus 2r times tjn plus 1 minus r tj plus 1 n plus 1 minus r tj minus 1 n plus 1, and this will equal our tjn plus R RTJ plus, no, actually this would be 1 minus 2R TJN because of these two similar values plus R RTJ plus 1 N minus R TJ minus 1 N. Yep. Okay, so now we're going to be using the von Neumann stability analysis to determine whether to prove actually that using the Crank-Nicolson differencing scheme is stable regardless of the choice of R that is used. So just von Neumann, and then utilizing some of the equations that we found in part C, specifically Tj plus 1 n equals Tikx times Tjn, where Tj plus 1 is equal to e to the negative alpha times k squared times t times the I kj plus 1 delta x, and our tj n, or tj minus 1, where e is negative ikx tjn. We're going to take tjn here, where we have basically the same exact thing. However, since we have a j here, and since this is adjacent to what we use here, we're going to have ikj times delta, oops, I already wrote x. Our next step is to now, basically we're going to take our equation up here and we're going to apply some of the same, our equation up here, and we're going to apply some of the same logic we just found, and we're going to essentially combine and take the difference of these terms, and that's going to help us prove the stability of our equation and why R, no matter what value you use, it doesn't exceed 1. So we're going to start with R, I believe it's negative, R E I K delta x times R TJ plus 1 n plus 1, I believe, and then plus R1 plus 2R TJ n plus 1 minus R REI K delta x times TJ minus 1 n plus 1. That's going to be all over TJN times RE R times E. It's going to be negative IK delta x plus 1 plus 2R, come out to TJN, and, oh no, we don't. Since we took out TJ, we don't need that. And I believe it's minus RE K delta x. I'm gonna double check that real quick. Okay, just a couple things we're missing. There's supposed to be a negative here. R n is actually n plus 1, and we have no plus 1 or minus 1 here. And after just canceling and summing or simplifying this down, we are left with plus 1 times r k delta x plus 1 plus 2r plus e I k delta x. Okay, so one thing to note, did make a little error. This is supposed to be a negative right here, not a positive, and it wouldn't make sense if it was a positive, as this would be the same as that. So it's supposed to be negative. And now what we're going to do is we're going to make a little ratio of sort, or I guess a differencing of tjn plus 1 over tjn. And what we find is r1 minus 2r plus r times e to the I k delta x plus e negative I k delta x over 1 plus 2r minus r times e I k delta x plus e minus I k delta x. And then if we simplify this down and integrate it so that our e is isolated, we find that our 1 minus 2r is plus 2r 2r cosine k delta x over 1 minus 2r minus or plus minus 2r cosine k delta x. One thing to note now, since we found this equation, this basically states, and this is what helps us prove that no matter for whatever r value we choose, it never exceeds 1, proving that it is a stable differencing scheme. So this, we were going to be using this and our von Neumann and our algebraic equation in our collab section, which we'll get to in a second. So now we're on the collab section of this. So what we're going to be doing is we're going to be simulating the time-dependent response of a 50 centimeter aluminum bar. And we're going to be simulating the results in about 20 time step intervals. So in Colab, I've already got our library set up, our print options, our R value, and the R value equation that we have here, and we use the values that we're giving in the problem statement to find that R equals 0.05. So to start, I'm going to state n equals 20 for our time intervals. Our so t equals np dot full and then 20. So we're going to go ahead and raise n to 50. And then, much like in part C, we had a initial temperature, which is already given to us here. So it says it was maintained at 50 and then 80 degrees respectively. So our initial, we're going to keep it at 50 for the change. And then 80. Next, we're going to utilize a matrix of sort. So we're going to be using something different this time. We're going to use VStack, and this will essentially help us solve our parameters without the need of redoing them by hand. So just do them all at once, which makes it more convenient. R np dot full and minus 2 1 plus 2 2 times R, and then np dot full. Gemini got it there. Okay, there we go. And then we're going to do something similar to what we did in part C, where we use our ID, or this line of code basically is going to be pretty much the same. P dot range n, and then fig equals make underscore subplots, and the fig dot add underscore scatter. It's kind of right, but idx y equals t, or mode is going to be lines, and then our name will be t initial, and then for n in range, and we're going to use 10,000. So now we're going to set our b equals, and we're going to basically use one of the equations that we found in the writing section. So 1 minus 2r times t, put 1 to negative 1 plus r times t. It's going from 0 to negative 2, and then r times t, but we're just doing 2. And then we're going to set our initial b, which is 0, and we're going to use plus equals r times t1, or sorry, this would be 0, and then we're going to repeat this, but for negative 1. Just change both those to negative 1. So now we're going to go ahead and define our t negative 1, and this is going to be using our np dot lineout dot solve underscore banded as stated in our problem statement. We're going to go ahead and make a 1 of 1, our matrix, and our b values. And then we're going to say that n is percent of 20, it becomes 0. Then we're going to run this fig.add underscore scatter, which seems like Gemini got it for the most part. A little wrong, but n plus 1. Yeah, I think that's about it. And then we're going to do our fig. I'm just going to press run all. Yeah, it's SciPy, not NumPy. Okay, there we go. Yep, so here's the graph that we're looking for. You can see that our temperature profile has that same linear relation as we saw in part C. So this is our plot and our simulation. However, for our final step, we want to make our time step 10 seconds to show that while the simulation at early times is inaccurate, the numerical solution remains stable. So let's go ahead and change this to 10. And as you can see, we have those inaccuracies right here. However, we do have that linear plot. So this goes to show our numerical solution does remain stable, even though we have these few inaccuracies within our plot.